Hello, my name is Andres Quast, and today I'll be presenting Lab 3, Black Hole, in Physics 2211 in section W14. So the purpose of this lab was to find the mass of a black hole that was given through the analyzation of a star's orbit, then using this to find the velocity a ship must have to not get sucked into it or stay stuck on the planet. Principles that I used in this were Newton's universal law of gravitation, in which I solved for the mass of the black hole, and you can see that F is equal to G times M1 times M2 over R squared, and Newton's second law, or the momentum principle, that is F net is equal to MA, or mass times acceleration. The results of this were that I got the mass of the black hole was 1.12 e to the 34th, and that the initial velocity that I chose for my spaceship was negative 9.43 e to the 7th, comma 2 e to the 6th, comma 0 meters per second. Newton's second law states that the net force is equal to dp over dt, and then you can see that the net force is equal to the perpendicular force plus the parallel force, where the parallel force is the change in motion of the object, which decides its speed, and it's also determined by the change in magnitude of the momentum, divided by the change in time by p hat, which talks about its direction. The parallel force is the change in direction, and you can see that in the future slides as we can see the planet changing its direction, or the star changing its direction, distributed by the arrows. The velocity update formula that I use is Vf is equal to Vi plus Fnet divided by m times delta t, and the average velocity is the final velocity because gravitation is a non-constant force. The position update formula that I use is Rf, or the final position, is equal to the initial position plus the average velocity times delta t, and Fnet is equal to Fg because we're in space and that's the only force acting upon the star at the moment. Alright, the system and the surroundings are the first one, where the system being the black hole and the surroundings being the star. The initial conditions obviously are the gravitational constant, and then we have the mass of the star that was given, and the time interval, which is the number of seconds in a day. Using Newton's second law to find mass, we can see the code below that shows basically in the middle you can see the how I calculated the parallel force, or the Fnet parallel, and then later on calculated Fnet perp, which is then used to find the mass of the black hole, just given by all of these different calculations and using Newton's universal law of gravitation. And this is what it looks like when you're running it, with the arrows pointing the arrow pointing to the wards. The center is the perpendicular arrow, or the parallel arrow is pointing in this direction here, and in this direction here, and then this is the Fnet. And below you can see the mass of the black hole throughout the whole time, and I'll explain why it isn't constant. So as you can see, here's all the mass of the black hole, with the average being 1.12, 10 to the power of 34, and I have it graphed here in a scatter plot with the average shown in the middle with this red line, and the magnitude of Fnet was 9 times 10 to the power of 28. Magnitude of Fnet parallel was 2.34 times 10 to the power of 28, and magnitude of Fnet perp was 8.7 times 10 to the power of 28. Okay, so the next part of the lab was to find the spaceship's velocity, and so the system you can see is the spaceship, and the initial velocity is what we were trying to find, and the mass is right here, and then the surroundings of the planet and the black hole, which you can see the properties below. The code for finding the net and the Fnet on the planet and the ship is seen below, where the Fnet planet is here, and that's the ship being held down from the planet's gravity. And then you can see the black hole to the ship, the pole that the ship has that the black hole has on the ship. And then you can see how we update the planet's velocity and position and the ship's velocity and position using all these calculations. So when you run it, it looks something like this, where the cyan line is the position of the planet, and the purple line is the position of the spaceship. I chose the initial velocity of negative 9.43, 10 to the power 7, 2 times 10 to the power 6, 0 meters per second as my initial velocity to escape the planet's orbit and get past the black hole. So one source of error that I had was that the initial velocity may not be optimized, just because I guessed and checked to find it. So what if the spaceship you wanted it to begin orbit around the black hole, well, it would look something like this, where it begins this purple line around the black hole. And to do that, you would need the y to be a little larger than the planet's velocity, and the x to be a little smaller, so that it can still escape the planet's velocity, but it would be able to begin orbit.